All right, so thanks for this opportunity, and sorry that I am not there. So I'm going to just walk you through the stochastic multi-cloud model, as Bichut mentioned. So I will roughly tell you about the design, how the multi-cloud model came up, and how it's been designed, and how it's been implemented in many GCMs. I'm not going to go through all the lists, but I will start from like very basic, simple models, and then build on to GCMs and so on. And I will show you some simulations that result from that. Okay, so this is roughly the outline. I will give you a bit of introduction and then talk about the three cloud type stochastic multi-cloud model, and then some tests using toy GCMs, as we call them. And then I will talk a bit, take a little detour to discuss about local interactions and how they are important and what they are important for. And then I will show you some implementation in CFS, and then extension to the Zhang-McFarlane parameterization. So I'm not going to give you all the details, that if you're interested. Oh, can you guys hear what I'm hearing?
Yes, we hear you. We also see the cover of the book called Models for Tropical Climate Dynamics by you.
There is some kind of, oh my God. Sorry about that. Okay, so yeah, so like I was saying, just this is the book that if you're interested to look at more details, and you will see a lot of other applications and so on. So for the introduction, just going to tell you a bit why we're interested and how all this come together. So organized convection in the tropics is what we're interested in, and the key idea or the key thing that we see is that it involves three cloud types that interact with each other and with the environment. And there's these three cloud types like determine some kind of self-similarity across scales for different types of waves, and including the Madden-Julian oscillation. And this whole thing is basically a sign that this is not something that the quasi-equilibrium can capture. This is a deviation from the quasi-equilibrium paradigm. That's why we need a build up, like from bottom up, cumulus parametrization to be able to get all these interactions across scales and the self-similarities. So this importance of the missing variability of the convection in GCMs that's not captured by the quasi-equilibrium paradigm or parameterizations. So adding the stochastic model will help do that. And in a sense, the stochastic multi-cloud model operates as a super parameterization, in the sense we try to get like the subgrid variability into the model, but instead of running a CRM, which is very costly, we try to mimic some kind of the dynamics or the statistics of convection in that way. So the multi-cloud model, why through the multi-cloud model? So this is the idea that comes from this paper by Deacon Johnson and his collaborators in 1999, when they discovered, or at least they suggested, that the tropics is not just shallow and deep convection, but there's actually also congestus clouds that are very important, and they basically are in the middle troposphere, like they detrain before they reach or right at the freezing level. And they basically constitute a big portion of the convection of the clouds, convective clouds. And there's this paper that came up in 2006 by Brian Mapes and other people, where they compiled a lot of different pictures from different papers which they all point out to these three cloud types that dominate different systems, starting from square lines that start with like shallow clouds and then congest as deep stratiform, and two-day waves that start with shallow, congest as deep stratiform, and also these are the two-day waves. These are more like mesoscale systems, and Kelvin waves also have the same structure, and the Madden-Julian oscillation as well. So these are all at different scales, but yet they have all the same kind of structure. And in observations, they are often seen as being embedded in one another, like the MJO is often seen as an envelope of synoptic scale waves, and the synoptic scale waves are sometimes have square lines and mesoscale systems embedded in them. So the idea is that to have this kind of embedded structures with the same kind of self-similar features is kind of impossible if it's not, if it's linear, because that's not going to be possible because these features are not symmetric. So then the idea is that this has to be some way of stochasticity that's to making this happen, so that the systems in front of the big system will have smaller or shallower clouds dominating the systems. The subsystems in the middle will have deep clouds, and the subsystems in the back would have more stratiform clouds. And this is what's known as the stretched block hypothesis that Brian Mapes and his collaborators actually came up with in this paper. So then the idea is that to build a stochastic model that can do this kind of stochastic or statistical features that will capture this nonlinearity in a way, and this kind of self-similarity that's highly nonlinear. So the idea is then to build that stochastic multi-cloud model, but then use it as a fix to cumulus parameterizations that typically assume the quasi-equilibrium. So then you use the stochastic model to break the quasi-equilibrium, and also add this kind of self-similarity and self kind of organization of clouds across scales into the parameterization, so that parameterization talks to the GCM, and the GCM forces the stochastic model, and so on. So why congestus clouds? So the idea we had is that you have this idea of dilute parcel lifting, where the parcels of convection, convecting parcels when they come from the boundary layer, if they encounter a dry environment where the saturation theta E has this kind of shape, when they mix with the dry environment, they lose buoyancy very quickly, so then they would detrain below the freezing level. But when the environment is moist enough, then it will look something like this, and then actually the parcels will entrain air that's not too dry, so they won't lose a lot of buoyancy, so then they can actually raise higher and exceed or go above the freezing level, so they will have actually a boost a buoyancy boost from freezing, and that you get deep convection. So this is the framework of the stochastic multi-cloud model. So it's a lattice model. So we set up a lattice, a microscopic lattice that's laid on top of the GCM grid box. You can think of the thick lines as the GCM grid, and then the thin lines are where you superimpose the fine lattice on the GCM grid box. And then the fine lattice basically sits this stochastic model. You can think of them as particles or some sort that occupy these small sites. And then they would change color depending whether they represent a congestus cloud or a deep cloud or a stratiform cloud. And then you transition from one cloud type to another. Then you can go from clear sky to shallow, or to congestus, or to deep, and then you can go from deep to stratiform. You can also go from shallow to congestus, congestus to deep, and so on. And this depends on the probability. This is random transitions, of course, but with probabilities that depend on the background, whatever kind of background you have. If you have strong sin, then you would likely have transitions to shallow convections are favored. There will be high probability transitions. But if you have CAPE and then the environment is too dry, then you will have likely transitions to congestus clouds. And then when the environment becomes moist, and actually congestus clouds condition the environment by moistening through detrainment and low-level convergence. So then they moisten the environment, and you would get transition to deep convection will be favored. And once you have deep clouds, then they would transition to stratiform, and then the cycle is kind of closed. So then we build all the mathematics. This is a giant kind of Markov chain that sits on a space, on a giant space, but it take only these 4 values, like 0, 1, 2, 3, and then you get the probabilities of transitions that you can set up very nicely to go from one type of cloud L to another type K, according to some transition rates. The rates are called R, and these R's now can be made dependent on the large-scale predictors, as we call them, like sin, CAPE, dryness, etc. So the philosophy is basically like I told you. So a clear sky site will turn into congestus with high probability if there is CAPE, and the middle troposphere is dry. A congestus or clear sky will turn to deep with high probability if CAPE is positive and the middle troposphere is moist, and so on, and the deep. And this is basically all. This is just the rules that we make up. And here I have only 3 clouds, but you can have the shallow clouds as in the cartoon I showed you before. Then you build up basically your Markov chain. Then you have a transition matrix or infinitesimal generator, as it's called in the theory of Markov chains, which is just a matrix that basically has all the rates. And then because there are some transitions that are not physical, we cannot make up stratiform clouds from clear sky, so we set up R03 to 0, and then we don't allow transitions from congestus to stratiform, etc., and we don't allow transitions from deep to congestus, or from stratiform to congestus, or from stratiform to deep, and so on. So these are just set to 0. And then, like I told you, all the rest rates are just functions of things like CAPE, dryness, and sin, and so on. And then they are modulated by time scales. This is like these are time scales. They will have units of time. And the idea is that these are units of time. They are reference time scales, if you wish, of these transitions of the cloud dynamics or transitions of clouds from one type to another, which roughly we know from just experience that they are on order of minutes to hours. They cannot be longer than that or much, much shorter than that. So, but of course, the devil is the details, so you need to know them if you want to do an accurate prediction or a good model. So what we can do, actually, this model allows us to infer them from data. So you can, if you have cloud data, like from radar or from larger dissimulations, and then you have the predictors that produce them, then you have a time series, then you can learn these parameters by doing like some Bayesian inference or something. That's what we call Bayesian machine learning. And we have algorithms to do it. And recently, we are making the algorithms to go faster, and we're trying to apply those to data from Go Amazon and also from Indian monsoon region and so on for various projects. So this is just like an example that we kind of made up at some point, and we tried to make simulations with. we can think of all these time scales to be order a couple of hours or some fractions of an hour, depending of what kind of transitions we want to make slower or faster and so on. So these are two examples that have been explored in the. Please interrupt me if you have any questions or anything. So this is really well-wired theory of Markov chain. So this is, we make it Markov chain that's ergodic, and for a reason, because these kind of models come from what's known as the particle interacting systems, like the Ising model of statistical mechanics, that are known to represent Hamiltonian systems. And we have a measure, an equilibrium measure known as the Gibbs measure. So this model, basically, you can compute that equilibrium measure. And here, when the rates are just known, you can compute that equilibrium measure, and the equilibrium measure depends exactly on, or specifically on, these transition rates that you have. Like here, will be like congestus, deep, and stratiform. This is for 3 cloud types, and Z is a normalization constant, and then of course it will depend on all the rest. And these are the cloud area fractions that you can come up with. Just if you simulate that stochastic model, you can count how many lattice sites are congestus. You divide by the total number of sites, you get the area fraction of congestus, and you do the same for deep, and you do the same for stratiform. And if everything is correct, if your statistics, if your math, your simulations, you have no bugs or anything, the math tells you that this equilibrium measure we have here is the expected value of this area fractions. So out of the bat, we know roughly the target of this model, what it is. If we know like the equilibrium or the climatology of the system we want to simulate, then if our model, the expected value, reproduce the climatology, then you are happy that actually you are already doing something good. So this is just one of the first realizations as we do. You simulate that lattice model, you give ourselves some CAPE and dryness values in non-dimensional units. And here we have a 20 by 20 lattice, and we run it with that stochastic Markov chain, and to like 100 hours here. And then you see these oscillations. This is deep convection, this is stratiform, and this is congestus, and this is the total of clear sky. So clear sky is just the complement of the cloud. So you just simulate the 3, and then the difference from 1 will give you the clear sky. And as the dashed lines you see, these are the equilibrium values that we can compute directly. As you can see by eye, the stochastic solution just oscillates around that equilibrium as it should be. So the expected value is that. So that's a good test or validation at least. But of course, there is one thing that you may already wonder, why we have all this lattice with a giant state space. How are we going to do this in a GCM? We want to do parametrization that's fast, not a super parametrization. Well, we don't do that in practice because you can actually assemble all these area fractions as you just count the number of congestus sites, the number of deep sites, and the number of stochastic sites, and then you can actually construct mathematically the stochastic model that just simulates the number of the total number of cloud types, and that's what we call the coarse grain process. And we can write them directly, especially in the case when we neglect interactions across local interactions between neighbors on the sites. And that's really just a counting problem. It's easy. You can compute the rates of change of the coarse-grained model, which becomes a birth-death process. Basically, we call it the birth-death process. With immigration, it means there are three populations, and then they just move from one country to another, and so on. So there is also birth and death at the same time. So I will come back to the case when there is local interactions. The things are not as simple as this, but actually the model without local interactions is already good enough that it gave us lots of good results in many, many applications. But the local interactions one has another purpose, which I will discuss. Okay, so one thing that we do nicely, like when we understand Markov chains and so on, you can write down what's known as the Kolmogorov backward equation, and the Kolmogorov backward equations for the birth-death process, for the total, or the numbers of cloud fractions of cloud types. It's just this giant matrix system whose solution is an exponential like this. And however, we don't really use this to simulate the model. We use it for the inference problem, but we don't use this for to advance the model, because this is also expensive. So instead, what we do, we use what's known as the Gillespie algorithm, which basically just helps you move your Markov chain step by step. And it's a very nice algorithm that everyone who works with stochastic models needs to know. And this is basically was motivated or designed first for chemical reactions. So the idea is that you have multiple chemical reactions, and then you have the rate of these chemical reactions, and then you have the minimum or the minimum time before one of the reactions happen, and that's basically will be the rate of the sum of the rates. So this lambda will be just the sum of all the rates of all the possible transitions, and this will give you a Poisson process, or rather, and that Poisson process, the first time it sits the clocks up, will give you the first time you get one of the transitions, and then you can simulate that first time. It gives by just 1 over lambda times log of a random number chosen from 0 and 1. And then once you have this first time of transition, then you can decide if that transition is bigger. If it's bigger than your time step, then there is no transition. But if it's smaller than your time step, then you accept it. You have one transition that's happening. So then you decide what transition is happening. Then it's just a conditional probability. Then you have three probabilities to choose from. Basically, you have 7 probabilities to choose from. You have to just now choose another random number, and then if it sits in one of these intervals that has length, the different probabilities that are associated with the different transitions, then you have your transition. That will be your transition. So this is a very, very fast and very efficient algorithm that we use in the models. So this is just to show you. I showed you that basically Markov chain Kolmogorov equations are differential equations for the probabilities. Now you can take expectations from this equation. You take expectations. If you take expectations, you get the mean field equations that are known as the mean field equations. These are basically now going to be differential equations ordinary differential equations for the area fractions. And here, it gives you, because there's no local interactions, it gives you a linear system. It's actually a damped oscillator. It will give you a damped oscillator. We compute all the eigenvalues of the oscillator, and they are all negative real parts, and then the imaginary parts are non-zero. They just oscillate. And the trick is, depends how fast the oscillations are. If your oscillations are much faster than the damping rate, then you will get long excursions. Then that basically tells you quasi-equilibrium is impossible. And that's the idea of how you can, that if the damping rate is much, much stronger than the oscillations, then you are actually going to, you can think of the quasi-equilibrium as being valid. And so this is just a simulation of the coarse-grained model, again, with the same idea. And then it just shows that the damping versus the non-damping, and then the solution to the ODE system is the equilibrium solution, the same thing as the equilibrium solution to the stochastic model that we discussed before. They are exactly the same equilibrium. So now, any questions so far? Okay.
Boualem, I think we'll ask all the questions at the end. That way it will be easier to pass on the mic.
Okay, good. So now I'm just going to show you some ideas about coupling the stochastic model. So we've been doing this for a long time, and we have a lot of ideas how to do it, and I will show you a couple of them. So there are also some groups who picked up this model and had their ideas, like the Peters et al. And Donsky et al. They basically took this area fraction that we come up with and used it to set up a mass flux and from a vertical velocity, and basically overcome the quasi-equilibrium this way. But there are many other ways to do it, as I will be showing in the next slides. So this is like the easiest one, where we do a toy GCM. That noise is back again. Oh my God, I think the Zoom is
Okay, maybe, because I think all the online participants are on mute. And
no, I don't think it's online participants. This is like pirating or something.
oh,
It's just me. I don't know. It's still here. It's really a movie. Oh my God.
okay.
But it's streaming a movie. It's not
It's a
me.
movie streaming. Can the technical team check if there is any?
Okay, now it's gone. I have no idea what's going on.
Okay. Okay, no problem. Yeah, you can share when you're ready again.
Where was I? Okay. Can you see now?
Again.
Hello?
Yes, Boualem. We can see the two baroclinic mode toys GCM.
Okay, so the idea is that we have two baroclinic modes where we have a GCM with crude vertical resolution, as we call it, where you have only two layers or two baroclinic modes, and which basically says that you project your velocity into the cosine z and cosine 2z, and the temperature, potential temperature here into sine z and sine 2z, and then you write down the equations, and then it will be just 2D or PDEs instead of 3D, but you have two systems, and we can use them to connect to the stochastic model. So the idea is we make these heating profiles or heating rates, deep congestive stratiform, and that go into the first and second baroclinic modes. And the first mode has mostly deep convection that's been that's there, but if these parameters actually can be set to 0, so then you can get only deep convection for the first mode, and then congestus will heat the low troposphere and cool the upper troposphere, and stratiform heats the upper troposphere and cools the lower troposphere. That's why you have a minus sign here. And then you have a boundary layer, theta EB, that responds to evaporation from the surface, and then downdrafts like from the upper layer. And then you have the moisture equation, that's just a vertical integrated moisture or average moisture that basically responds to divergence and precipitation, and then the downdrafts that basically come from detrainment and that moisten the atmosphere, the free troposphere. So that's the heating profiles. Like for deep convection, we set a profile like this. For congestus, it's like this. It cools above, heats below, and then the stratiform is like this. And then this is the idea of the stochastic model, where you have transition from shallow to congestus to deep to stratiform. And then we have formulas for the heating rates, as we call them. HC will be like low-level CAPE times some factor that's just normalization factor, and dimensional constant, and then the area fraction from congestus. And then the deep convection also obeys the same idea. Then you have like the area fraction of deep is here. It comes as an inverse here. And then this is theta EB, like the boundary layer potential temperature, which this you can think of this as CAPE. And then here you have the moisture, and here you have the temperature in the mid-troposphere. This, you can think of this as some kind of an adjustment. So this is like a potential for deep convection. And then we have the stratiform that obeys another equation, which is roughly just a fraction of the deep convection, but also has to obey that it's proportional to the fraction of stratiform. And we run that model. This is just simulations where there is no like horizontal dependency, where all the horizontal derivatives are set to 0. We call it single column run. You get this kind of oscillations for θ1 and θ2, and then theta EB, and then you get congestus, deep and stratiform, heating, etc. But what I want you to pay attention to, this is the cloud area fractions, where you get congestus peaks followed by deep, followed by stratiform, and so on. So this is kind of the same story that happens all over as we will go through. These are simulations with that model with the horizontal dependency, where we set up a worm pool, and then we just let it run for up to 1,200 days here, and then time goes down, and then you get these kind of waves, like gravity waves, propagating away from or in the worm pool in both directions. And when we filter this kind of waves, we see this kind of behavior, where you see like this is first baroclinic velocity, second baroclinic, and θ1, θ2, and this is like theta EB, and this is in green, and this is moisture, and you see like a peak, theta EB peaks first, and then moisture, and so on, and then you get deep convection sets here. This is the area fractions. You see the congestus starts in green, it oscillates, and then it's followed by an oscillation of the deep, that you see like the deep is weak in front and then gets stronger and stronger as the congestus gets smaller, and then the stratiform follows up, and then follows, and then lasts afterwards. And you see the heating, this is the congestus heating, this is the deep heating, and this is the stratiform heating. And this is like the profile of the waves. You get this nice tilts. This is the heating. You get stratiform heating in the back, congestus, then deep, and then deepening, and then stratiform, and you see the tilt of the temperature and velocity profiles, just like the ones I showed you in the beginning from the MAPES paper. So this is all encouraging. Now I'm just going to, how much time, how am I doing in time? Still have?
I think we have like we can have like 10 more minutes for you to
have questions?
Yeah, but I mean, I'm just keeping another 10 for like people to ask questions.
That's what I'm saying. I can go 10 minutes and then 10 minutes questions.
Yes.
Good. Okay, so let me talk a bit about the local interactions. So what the local interactions are important for. So they will be one way to emulate self-organization at the small scale, like at the scale of the GCM grid box. And then you can look at mesoscale systems, like in the Eastern Pacific or coastal convection, if you're interested in the systems that propagate along or across continents to the ocean and so on, and vice versa, or shear organization, sea breeze, and so on. But you can also look at cloud-cloud interactions, how which ones favor or in favor organization of convection. And this mainly important if one looks at the gray zone, where you can have these convection systems to go across GCM grid boxes. Like if you have GCM grid box about like 20 or 50 kilometers, then the systems can actually propagate from one GCM box to another. So it's important to have this local interaction so you can capture those. And that's the idea. So how will you do it? So like I was saying about the Hamiltonian system. So here we write the Hamiltonian system in all its glory. So the idea is that there's this potentials, and the potentials will have like local interactions. So each K and L as before, these are just the cloud types, and I and J are the locations of the sites. So then there will be like interactions that will be depending on the how far the sites are away from each other, and also some kind of matrix J of local interactions. And then you can write down the rates the same way as you do it before. Here we can write like the Gibbs measure, and we differentiate the Gibbs measure, and we get this kind of relationships. We get like the rates of going from clear to congestus plus clear to deep to be settled with this kind of equation to rates of depth of deep and depth of congestus, and also transformation. So these are known as the balance, or these are not detailed balance. These are balance equations that guarantee that the Gibbs measure is an equilibrium measure to the system. And this now used as an so this is the Gibbs measure, and this will be used as a design principle to write down what this rate should be. And then, so like I said, you can just now write everything, and then we add the local interactions. Then we can actually write the mathematics and coarse-grained even this local interaction case. But now we have to make some kind of assumption. And the assumption we make is a uniform redistribution of particles within each like GCM grid box. Then we can get this like coarse-grained potentials, where now there will be dependency on the neighbor. So this is like the GCM grid box, but then this is the potential, and this potential now depends on the neighbors. Like here, S means south, and east means like east here, and etc. Southwest, and you can have dependency on all what's happening in the neighbors. So the ends are just the total number of clouds of type L here in this cell, or this cell, etc. So then this will retain the interactions at the coarse grain level, although you have, but then we can also write down the mean field equations the same way as we did it before, by just taking expectations. And here the mean field equations will be very complicated. They are actually nonlinear, as you can see here. And the nonlinearity comes from these coefficients alpha. These coefficients alpha are actually convolutions. They are convolutions, and they have very, very complex behavior, but like dependency. So this is what convolution is. But we can do some kind of approximations and write them down in a simpler way, and we can get some nonlinear equations. And in one paper, so we can, this is like testing that model, which with local interactions, without local interactions. And if you can see difference here. You can see this clumpiness in the case with local interactions by just assuming an interaction matrix of this sort. So this means that the congestus clouds will be favored to clump with each other because this one is the largest of them all. So then that's what you get, this blue patches here. And that's basically just to tell you that you can really do things to the model that if you wanted to behave a certain way. So then we can run it again. You can run now for this picture here, we can see this is the simulated model, and this is the expected values, like in the dashed lines, or the solutions to the mean field equations, which is the same thing. And these lines here is what you get with the same parameters if you have not had local interactions. So this is what this is saying, that local interactions can actually change the climatology. So you can actually have a completely different solution in the long run if you add or not the local interactions, which means the subgrid scale dynamics are very, very important. So we use this to like I said, it's important to do like some of the gray zone. We can propose like prognostic stochastic closures for mass flux streams. And there's this paper where we suggest what we call a stochastic relaxation of quasi-equilibrium. And for the quasi-equilibrium, we have, I cannot go in 10 minutes, I guess I have much less than 10 minutes now, to all the details. So you have like the kinetic energy and the cloudwork function that form a system known as the energy cycle. And this is where the quasi-equilibrium came from. And the idea is that the cloudwork function consumes, the energy is consumed very fast by the large scale. So you get equilibrium within one time step of the GCM. So then this equation becomes steady. And then you solve for MB for the cloud-based mass flux. What happens is that actually you get an integral equation of this sort, which is when you discretize, it becomes a huge linear algebra problem. And that linear algebra problem is actually ill-posed. It's ill-conditioned. So basically, it doesn't give good solutions or stable solutions. So that's why there's lots of menagerie of schemes like relaxed Arakawa-Schubert, Zeng-McFarlane, where they change the cloudwork function with something else like CAPE, or they just go completely the spectrum of clouds and use only like one cloud type or one bulk plume. And so what we did is we just used the stochastic model, and we have the two large the energy cycle equations, we can transform the kinetic energy into an equation to the cloud-based mass flux through like kinetic energy relation to vertical velocity. And this is done in Penn Randall. And we get this kind of system. This is like an ODE system. Now the area fraction, here we assume only we have one cloud. It comes up as but with local interaction. And it comes up as a nonlinear equation. This is an exponential. And these are like potentials that you can think of this as being sin, H being sin, A being the cloudwork function, and U0 is the local interactions that I was talking about. And then this will become like a Lorentz system for moist convection. Indeed, this has multiple equilibria, and there are some regimes where it has one equilibrium. So this is the area fraction. This is the equilibrium as the forcing increases. For small forcing, you have an area fraction that's very small. For large forcing, that area fraction goes close to 1, actually converges to 1. If you give a strong forcing, then you saturate the model or the plume. And then this equilibria, they are stable for small forcing or for small area fractions, but then they are go unstable at the intermediate forcing, and then they become again stable at the log forcing. So if you are near 0 or near 1, you're stable. But you are anything in between, like the values of F from here to here, which roughly like from here to here, you will get really unstable solutions. The solution is unstable, but it's highly oscillating. You get some kind of Hopf bifurcation. And that's what gives this kind of oscillations. And then you can see small scale oscillations, and the F is oscillating at the same time, like a large scale oscillation, but then you get tiny oscillations on top of them. And that's what you get. You don't just get a periodic solution, you get some kind of very weird like complex limit cycle like this one. Or this one, if F varies from 10 to 40, it varies F from 0 to 10, like the oscillations of F. And then if we go to stronger local interactions, it becomes even different. You get multiple equilibria as F varies. You get an equilibrium, small area fraction. Then it goes to a regime of multiple equilibria. And then an equilibrium with just one equilibrium, just a single equilibrium. And then there are 3 eigenvalues for the 3 different solutions. For this one, you have this equilibrium, it's stable in the beginning and then becomes unstable. This is this solution. And then this solution here, it's always unstable. And this solution here is always stable. And then this is the cloud work function with the 3 equilibria. You get a cloud work function that increases, and then it decreases, and you get 3 solutions. And then the higher equilibrium here has a slower, smaller. Even F is increasing, the cloud work function doesn't actually comes down. You get this kind of hysteresis kind of happening. And here, what you get when you run the model, you get even chaotic behavior. You get these kind of oscillations are very wild, are not like just the periodic oscillations from F. And you get this kind of systems, like a chaotic system, like a strange attractor. This is not like a Lorentz system. It's more like a system known as the Rosseler system. It's very well known in the theory of dynamical systems. This has a very weak nonlinearity. The nonlinearity is only here in the Z variable. And then you get this kind of, this is the solution from the cloud model. This is not, if you write the solution for this, it will look like this. So what you get, the solution just oscillates here, turns around, and then from time to time, it makes an excursion up and then comes down. That's what it does. So this is when F is from 0 to 10, and this is F varying only from 0 to 5. So if you make F too strong, then you get much often like excursions. So this is kind of what happens in for convection, so it cannot be quasi-equilibrium. You get all this kind of excursions and so on, like very slow, and then it goes fast. So like I said, this is an implementation in CFS that we did. This is like the work of Praturi, basically. I think Praturi will tell you more about this probably. He could. And there we just did the same thing. We just imposed these heating profiles. I'm just going to show you some pictures where we go. This is like the climatology. This is the controlled CFS. This is the SMCM. This is from TRIM. And you see like the climatology is similar, but there are some small improvements. The big improvements we make are in MJO. Like this is like the CFS control model. This is now the stochastic model. See, look at the MJO here. Look in the observations. Look in the control, Kelvin waves, etc. This is really just is another nice picture which shows the rainfall distributions of from OLR and rainfall on this axis. OLR on this axis. This is from observations during the summer monsoon. You see like this kind of distributions, high rain rate that happen at lots of kind of OLR values in the model. Everything happens at small OLR values, and also it's confined. Kind of you have lots of low frequency of low rain events, and then the SMCM really captures better what's happening in the real world. I think I will stop at here because I don't think I have 10 minutes left for questions.
Thank you. Thank you, Boualem. So, do we have any question?
I can show you this movie that Praturi made. So this is the stochastic model. This is observation, and this is from CFS V2, and this is really this is the Madden-Julian oscillation as it propagates along the. So I'll be happy to answer questions.
Hi, Boualem. This is Eric Maloney. Good to see you.
Hi, Eric.
So you mentioned in one of your previous slides that this might have great applications for the coastal diurnal cycle.
Yes.
And I'm wondering, in this particular model, did you look at any changes in the diurnal cycle with implementation of the scheme?
Well, with the implementation of the scheme, did we see any change in the diurnal cycle? That's a very good question. So we have not really looked at the diurnal cycle in the model, like in the GCM simulations. We have not implemented the model with local interactions. We looked at the coastal convection and with diurnal cycle in a very, very simplified model. And there we didn't even have the local interactions. But it's all related on how the grid scale resolution we're doing, like the multi-cloud model, how the feedback from the large scale. So what we saw there, we were able to simulate, it's a paper that's been published a couple of years ago. We were able to simulate like the mesoscale systems and the sea breeze. The timing of the diurnal cycle was improved, but not by a lot because we don't really have the local interactions added. But what we improved, or what we saw improving, is the timing of the sea breeze. That actually was improved, but it's not because of the local interactions, because they were not there. I guess I didn't answer your question because that was not really the purpose of what I was saying.
Thanks, Boualem. That was good.
You're welcome.
I have a question, Boualem. Vishal here.
Yeah.
So I see that this is a beautiful model, beautifully put together. I was just thinking from an observational point of view, how can we verify the timescales of transition across modes? Or I see nicely that without really doing any strict coding for it, you still get that tilted structure. So
Yeah, the tilted structure is really built into the model, and the time scales you're talking about. So, like I said, we roughly know the bulk, like what kind of values you need to put in, but we don't do only that. So I was mentioning at some point Bayesian machine learning, and we are doing that a lot. And so we can actually make Bayesian inference from radar data of cloud area fractions, and we can use the time series to build like the likelihood probabilities for the timescales. So then you can run the model, and then basically compute the probability, the likelihood of the timescales of the observation to be reproduced by a given timescale. So then you can then infer what timescales produce the observations. So we are doing that like crazy. It's very, very slow because we have to do it with Markov chain Monte Carlo, which means you have to run very, very long Markov chains to get the distributions correctly. And that's now we are designing what's known as the synthetic likelihood, where it's much cheaper to construct a surrogate to the likelihood function, and that's actually working well. It's still work in progress, but it's working well.
Thanks. A follow-up question to that is, you get that tilt right, and there's also a spatial tilt I felt that is captured in this model. So I'm kind of thinking about the vertical tilt of systems that you get right in this model. I was wondering, how does the spatial tilt? It's kind of emergent out of these interactions, right? The tilt.
So the model has these transitions. They go you transition from like clear sky to congestus, if with high probability, if the atmosphere is still dry, but you have CAPE. So then what you get low-level heating. And then the congestus clouds will moisten the low-level troposphere by detraining and also by converging moisture. And when the low level is moist, then you start making transitions directly to deep or making transition from congestus to deep. So now you get a progressive deepening of convection. And that basically, when you look at the timing of that, and if you have a wave that propagates, you will get a tilt. That's automatic. And then the deep convection, then of course, we transition to stratiform, and that also will give you the tilt to the back of the wave. So you get the tilt. It's kind of built up, but of course, it's the large scale predictors that are telling the model to make congestus, to make deep, to make stratiform, and that's basically based on this intuition on how the multi-cloud organization happens through these systems. So that's what I say, it's kind of built in.
But I thought I also got the impression that you also get the spatial tilt that you initially showed in the
what?
You also get the spatial.
Yes, because the wave does that, right? Because you have a wave. Okay. That wave has an envelope where it moistens at its own scale, right? It's dry at its own scale, and then you get also local systems. The local systems come directly from the grid scale, from the model itself, from the stochastic model that's operating at the grid level. And then, so that gives the memory at the small scale, but that also preconditions the wave. And then the wave modulates what happens at the small scale. Then you get this kind of modulation that I was showing before, right? I think you are referring to this.
Yeah, yes.
So
yes.
you get this kind of modulation. So if you look at this as just its own system, it has both congestus and deep, but the congestus is much, much bigger. But then the wave is telling it to make more deep in here, but less here. So the wave is modulating how the system, how the small scale or the scheme, the stochastic scheme is making the different cloud types because of the predictors, like the large scale predictors that put into the rates. So these rates here are functions of cape and dryness, etc. So these are large scale measures or large scale predictors. So they tell the stochastic model what kind of probabilities it will have or transition probabilities it will have. So that you can think of there is an equilibrium distribution or a distribution that basically changes with the large scale dynamics. Like it's slowly varying equilibrium measure, and that equilibrium measure is being sampled at the same time, all the time, very fast. But by the stochastic model, but that equilibrium measure is varying at the large scale, with the large scale dynamics.
Yeah. Thanks, Boualem.
Hi, Boualem. This is Vidyut. I have a very small question. I would request you to quickly answer it because we are already over time. So, so the basic, three basis functions: the deep, stratiform, and congestus.
Yes.
So we were listening to Courtney yesterday, and we learned that trimodal structure is more valid for oceanic regions than over land, if I remember correctly. So have you ever noticed any contrast in performance of SMCM over land versus ocean? Or did you?
Well, yeah, I mean, that's a good question. We did not really look at specificities of congestus of the performance over land and ocean. As you know, we looked mostly at the MJO and convective coupled waves, and these are mostly over the ocean. I mean, most of the time. So, yeah, I don't know. So it's probably true for, I will suspect, things like mesoscale systems that would be very important. So what is she suggesting? That there would be more like deep and stratiform only, there is no congestus and things like that.
Yeah, I don't know. Maybe maybe we can discuss later.
Yeah, I think the thing, in terms of the model, it's not a problem.
Yes.
Because if the large scales is telling the model not to make congestus, then you won't make congestus.
Yes.
So it can survive with just on two clouds, right? So the thing is that you may need to modify the model to, if you know something that it should be happening over land, just because it's over land. But I think it should be embedded in the dynamics, in the large scale predictors. For instance, if over land, Cape is so large that it doesn't care if it's dry or moist to make deep convection. And that's typically what happens. Then you just basically need to have your transition to deep convection to be oversensitive to Cape, and that's actually is going to happen if you do the inference properly, like the Bayesian inference. Then what you're saying is basically when we make the inference, we have to be careful not to make inference for the ocean and then use it over land. We need to use inference over land, inference over the ocean separately, and that's actually what we have in the program, anyways.
Okay, Boualem, I'll have to stop you there. We all would like to thank Boualem again for staying late for us. And yeah, thanks, Boualem.
Bye. Thank you all.
Bye.
I need to stop sharing.